Welcome to today's lecture of SLP. Sorry for being a bit late, and I hope that this works now. So I'm in a new location, and this is a bit interesting now with this new setup here. I transported the entire setup to Germany. One question right away: is the microphone volume fine, or should I turn it up? If it's fine, then I think we're good to go. So I prepared a Menti for the start, just to get back into the topic. And I think you should be able to see the... Do I share the Menti? Where's the Menti? Ah, yeah. So this is clearly not the Menti. Let me see where it is. Here it is. Yes. Now we can see it, and I will also take off the headphones because I don't need them because I can't hear you anyway. So if you want to say something, just write it in the chat at the top, or I will also open this chat on the side so that I can see it, because here in this location I don't have a second screen, unfortunately, but fortunately I have a laptop. Okay. Sound and webcam is a bit out of sync. So if it's a lot out of sync, then I will try to fix it. But if it's only slightly out of sync, then I tried to get it better for the last 15 minutes, but it was a bit difficult here. A different sound card because I didn't take all the parts with me. Only the most important parts. Okay, let's start right away with this Menti, and I will just do that right away here. So I have two questions, and the first is a warm-up question. We will just wait for everyone to join. Okay, 29. Wow, we still have room for more. And I hope everything works actually, because this was now in a bit hurried action to get all of this prepared. And someone wants to do, so there's something with logs and processes. Of course, if you have wishes what we should work on today, just go ahead and post it in the chat or in the Menti Q&A. And I would say we are ready to start. And as always, check your phone so that you are really sure that you see the question at the earliest possible point. Starting the quiz. Segmentation faults. And this goes back a few lectures. We saw this already. Segmentation faults are something bad or are something to be afraid of, are helpful for debugging, for instance, a null pointer. Segmentation faults in a child process also affect the parent process, or segmentation faults are dangerous for the system. There's some seconds left. And if I know, so if you post in the chat if my sound is too early or too late, I will try to fix it, of course, on my side. Okay, so segmentation faults, yes, they are most of all helpful for debugging. Okay, and let me just try whether I can make the sound a bit better. Hope it's more in sync now. Okay, so let's continue. We will have a second Menti question at the end. Actually, can we do that now already? We can do that now also right away. I mean, Unmap, we covered Unmap already to a large part in the last lecture. And today we will continue there. Maybe we will use some locking together with Mmap. I think that would be a nice idea. Mmap can provide access to the memory of another process, or Mmap cannot create shared memory between processes because shared works using Smap. Mmap can map files into memory for more convenient access, or Mmap can only create small memory mappings. We've done one of these in the last lecture. Yes, we mapped files into memory for convenient access, and that was quite nice. I will show that to you again in a second, and then we can see how nice this was. Provide access to the memory of another process. It's not actually the memory of another process. You don't really map the memory of another process into your memory. Maybe there are some exceptions. For instance, if you're a root privileged process, then there might be some capabilities where you can do that. But in the most generic case with Mmap, you cannot just map memory of another process into your memory. Okay, restarting the stream. I hope you're back in the stream, so sorry for that. Yeah, lots of interesting technical problems today. Let's continue right away with resolving ones that's the fastest. So we have in first place Luki. Congratulations for that. And behind that, Alfredo and Clippy. So a very close one. Okay. So I would say, let's continue. Q&A. Yeah, Q&A. Let's go back to this question, this slide here, because now I can show the Q&A. Can we do something with logs and processes? Of course, let's do that. Why not? Close the Q&A, open VS Code, and we will start with that, because we don't have that much more content on Mmap if we don't consider logging. Maybe we want to consider some of the arguments there. So here we have a simple example that we used really a long time ago, right? We had this buffer where we generate numbers, and we generate numbers up to 1 million, and they should all be summed together. So we remember that this would would run some time. So let's check out how this worked. We compile this again, main C. We have to provide some argument here, pthread. This worked. So let's run this. Okay, so this takes some time, but we see that we actually implemented that correctly in the end. So this is working with pthread create and not with shared memory. So let's change that. Let's rewrite this example so that we are using shared memory. First thing that we want to do is we want to change this buffer here to shared memory. So let's do that. We have now a volatile size t pointer buffer, and we initialize this to 0. And we later on want to create a buffer of that size. Okay, so let's do that. We can just go here and create it here with Mmap. We know Mmap already, but I want to look it up in the main page again, just to be sure. So maybe I want to, maybe before I do that, I want to save this one in a new file. So let's call this main shared. Okay. And now we do the same things again. Buffer, size t pointer buffer. And that one we will initialize with mmap. Buffer. The return value of mmap is a void pointer. Let's check what the return value is. The return value returns a pointer to the mapped area. Okay, so let's check that. So we need some arguments for mmap. We have address. The address suggestion would be 0. Then the length, the minimum length, or in general, the length should be a multiple of the page size. The page size on our modern systems is usually 4096 bytes, 4 kilobytes. So that means we put 4096 there. That's the smallest size that we can allocate anyway. Protection flags. We need to check the protection flags. Again, we want this to be readable and we want this to be writable. We want this to have, different flags here, right? Flags, let's check flags. Map shared, yes, definitely shared. Map shared. And we also want to map this as anonymous. It's not backed by any file. Let's try that. Map anonymous. Okay. So the next one we have, we should not forget our include. We should add that one. And this is really a helpful exercise if you do that yourself. Take a program that you already have that uses multi-threading and just rewrite it to multi-processes. So we have map anonymous here. So we then need the file descriptor that should be -1, the man page said, and the offset 0. The offset doesn't really make much sense for map anonymous in most cases. For a file, this can be really great because if you say you don't need the first few kilobytes of a file, you don't want to read them anyway, you can just provide a different number here, like 4096. Again, multiples of page size would be great here. So something like 3 times 4096, then we skipped the first 12 kilobytes of the file. In this case, we just want to map memory area, and that's it. So now let's just check whether this still works. It should work because we are allocating memory instead of in this global variable now as a shared variable. Another part that we should do, of course, is at the end. What do we need to do at the end? So there's mmap, but there's also munmap. So let's check. The munmap system call deletes the mappings for the specified address range. Oh, that's super interesting here. For the specified address range. That means that you can basically unmap an nmap range in multiple separate calls. So this is interesting because that means that you can have one mmap call and then 2 munmap calls. Okay. And it causes further references. References means accesses. Accesses to addresses within that range to generate invalid memory references. Okay, so they are invalid memory accesses. If you try to access addresses in that range after the munmap call, then they will be invalid memory accesses. The region is also automatically unmapped when the process is terminated. Oh, so we don't even need to call unmap. On the other hand, closing the file descriptor does not unmap the region. Yes, I think that's something we saw already last time, that we closed the file descriptor, but the mapping still persisted. Okay, so the region is automatically unmapped when the process is terminated. So because there was a question on Menti, let me just show that to you. There was a question on Menti saying, oh, maybe it was it on YouTube? On YouTube, yes. How do we properly unmap or unlink shared memory? So unmapping happens automatically. You can do that by hand, but it's not necessary, right? So of course, best practice, well, you could unmap here. Is it best practice? I mean, it's cleaner if you do that. On the other side, if you, probably before the pre-thread exit 0, on the other side, if you do that before the process terminates, then it really doesn't matter. The region is automatically unmapped when the process is terminated. So the address must be a multiple of page size. Okay, so we can only unmap page size aligned regions. So the address must be a multiple of 4096. But the length doesn't need to be. So this is a bit weird. So with that, you can control how much of the memory is written back to a file or something. It's a bit of a special case that will give you some headache in operating systems. We don't care about that case for now. We just say length has to be a multiple of 4 kilobytes, and that's it. All pages containing a part of the indicated range are unmapped, and subsequent references to these pages will generate zigzag V. Yes, okay, so, but this is actually just repeating what is up here in more technical speech, right? So it generates a segmentation fault. Mmap and munmap are pretty much like malloc and free, just for shared memory or file mappings or anonymous memory mappings. Oh, you can't see VS Code. Yes, I will show it again. So I was just going through this sentence here. Yeah. It is not an error if the indicated range does not contain any mapped pages. Oh, so we could do something like an unmap with the null pointer. Why not? It does not contain any mapped pages. Fine. It's not an error. So on success, mmap returns a pointer to the mapped area. On success, an unmap returns 0. So we are not really interested in a return value. I mean, will it fail? Probably not, because we don't make any mistakes, right? It's of course best practice to check the return values, but in this case, I will skip this. So what do we have? We have our mmap call, we have our munmap call. Let's try whether it works. Probably we should run main shared. Oh, and it doesn't work. Discards volatile qualifier. Do we need the volatile qualifier at all? I mean, we are just using pointers here. The compiler can't really assume anything across different programs anyway. So let's see. The other option is, of course, to say here it's volatile and to cast it to size t pointer or to a void pointer down here. That would be the other option. And okay, yes. Or maybe this is a bit nicer. Let's run this. Oh, segmentation fault. Yes. Why do we get a segmentation fault though? Let's check. Let's run this with GDB. Main shared. So we run this with GDB. Always a good skill to have to run things with GDB. We backtrace this and we can see what happened here. Producer crashed. Producer pthread create. Oh, we need debug symbols. A common mistake is not compiling with the -G flag, and then you can't see any debug information. There was also a question in the chat, why even closing the file descriptor then when it does not make any crucial difference? Yes, I mean, it occupies some memory while you have it open, and the program might only be able to open a limited number of files simultaneously, especially if you're running in a sandbox. But in general, yeah, doesn't really matter. So let's run this and let's see where it is. Backtrace, oh, interesting. Buffer at index equals generated number. So this is bad. Let's check out what buffer is. Buffer is, looks like a valid address. Why would this generate segmentation fault? Let's check out what buffer index is. Buffer index is 0. So this looks totally fine. So I think the thing that we forgot, or the thing that we might have forgotten, is to tell the system how large this area should be. Maybe we need to f-truncate it. We can also check out the man page for Unmap on that. So we create the mapping, map anonymous. Does it say anything about f-truncate? Anonymous. Not backed by any file. Contents are initialized to 0. Okay. Let's check out whether it says anything about f-truncate. Nothing. Yeah, I also thought we need to use f-truncate only with the file descriptor. I mean, what would we use it on now? We don't have a file descriptor. So why can we not write to this location? It's prod read, prod write, map anonymous. Should be fine, actually. Let's run this again and check again what is going on. So it's a segmentation fault. We have this in line 55. Here the buffer is not accessible for some reason. Let's do this. Print what is there at this location. Okay. There is a number there. Let's do this just to print. Okay, so this also doesn't look very useful. Ah, yes, of course. So the buffer here, the buffer was never initialized. Let's maybe do that. Let's initialize this one to 0. Memset buffer. We don't know how memset works, so we will just look that up. And then memset. Memset takes a pointer, character here, and a number of bytes. Okay, so we fill this with 0, and we need this for the first 4096 bytes. Okay, not makefile. Okay, we need string.h. Okay, and yes, so this one also should be casted. Let's see what the reason could be that this one crashes. Run. Actually, yeah, this is again crashing. So we have a segmentation fault from thread 3. Thread 3, backtrace. Okay, print buffer. Print dereference buffer. Looks fine, basically. So this doesn't look like we are not allowed to access it. +2, +3. This looks reasonable, but the numbers are a bit weird, right? Because I would expect that this would be a size T buffer. It should be initialized to 0. But it's also not crashing here, so we can definitely access it. Of course. Now we set ourselves a trap. Look at this. We are unmapping the memory region here. And I just read to you a few minutes ago that after unmapping, trying to continue to access it leads to a segmentation fault. We are seeing now exactly what the man page just told us before. Okay, let's Let's comment out this line. Let's see what happens. So we run this, and it works. Okay, nice. So now this is operating in shared memory already, but these are just threads. So we want to change that. Okay, fork if, well, let's call this PADT, well, P1. If P1 is 0, then it's a child, right? And then we just call the consumer function. Otherwise, we have here PIDT P2. Also forks. And this one calls producer. And this one here, pthread exit, if the parent dies, if you remember from processes, if the parent dies, then also the child processes die. So we have to be careful there. So maybe we can just wait for the child processes. Wait PID, and we will wait for P1. Let's just check what wait PID looks like. Wait PID. We have to include some headers, of course. This is a nice little exercise to rewrite a program that was not using multiple processes to using multiple processes, and then and then we are able to see whether it still works or not. And if it does, then, then we were able to rewrite a program from single process to multi-process. Let's see what happens. Okay, T1 is unused. Yes, I'm not using T1 anymore. Okay. So I don't know whether this works now. Shared. Started it now. This seems to be running for quite a long time. What's going on here? Ah, yes, of course. They are stuck somewhere. Okay, so let's debug maybe where they are stuck. If we don't know, and let's just run it with GDB. Run. Okay. Backtrace. Oh, backtrace. Okay, where are we? We are in the producer. So we are creating one child process here. This child process we'll call the consumer function. And the consumer function, does it return? Well, if it returns, we should probably call exit 0 here, just to make sure that nothing bad happens afterwards. Okay, exit 0. Maybe that's an idea. But this one appears to wait for a semaphore. Can we attach another process? So this one? No, don't kill it. And then backtrace. So, okay, so this one. Okay, maybe I will open multiple terminals now. And I can just run GDB with a PID. So there's some tool to run yes, with -p process. Okay, and here we saw the process IDs, right? So this one showed us it's GDB -p 19820. Okay. Oh, okay, so this one says you're not allowed to do that because you're not a root privileged process. So let's run this with sudo. Okay. Okay. Oh, this is also interesting. Even with sudo, it does not allow that. Could not attach to process. If your UID matches the UID of the target, check or try again as root user. This is a zombie. The process has already terminated. Wait, if it already terminated, did anyone print a number? No, right? No one prints a number here. So this is really not looking like it's working. That's really bad. And one thing that we need to fix here definitely is these semaphores here. We didn't move them to shared memory. They are still here, global variables. No one can access them. So let's make them shared variables. So this is actually not a new camera. I just changed the location and the lighting is a bit different here. Okay. Okay, so let's see. I will change this maybe into a struct. I will call this struct logs, and I will just move them in here. And we check those buffer log statements here, and it's always then logs dot something, because I moved them into a struct. The next step is I will make this struct a pointer. Okay. Sound is still too fast. I can still try to delay that a bit. So let's try whether it's better now. Okay. And what do we have here? I mean, the sem init now works, and this struct. Let me make this a struct pointer. But I never know how this struct stuff works, so I will type this into log struct. And then I will say I have a log struct pointer logs. Yeah, this looks better. Oh, I have a lot of windows here. Let me just close a few of them and compile this. Oh, this doesn't work. Logs is a pointer. Did you mean arrow? Yes, definitely. Logs pointer. Should be this everywhere. Okay. Interesting. So what do we have? Implicit declaration of exit. Well, include standard lib h. Yes, sounds like a good idea. We should do that. Include standard lib. Compiled. Running this, it's seg faults. Of course, because this one is not initialized. So what do? We need memory for that. So let's allocate another buffer with its logs, and we cast this to a log struct pointer. We again allocate 4 kilobytes of memory, but they are now separate allocations, pretty much like malloc. Let's compile that. Still segmentation fault. Okay, so we have, yeah, of course, we are accessing the logs up there already. So let's do that after the mmap. Better, but still not working. So it's still not working. And one thing that we haven't done so far, if we take a look at the sem init man page, it says here the p shared argument indicates whether this semaphore is to be shared between threads of a process or between processes. So it means p shared, process shared. We want this to be process shared. So let's do this. Let's change this to 1 and see what happens. Yeah, something happened, but the sum looks really, really broken. Okay. So we are getting somewhere. But the other process is not terminating. Okay, so this doesn't seem to work really reliably, but at least it's a start. Okay, so we have our logs here. Do we have to mem set the area maybe to 0? Probably not, but it doesn't hurt if we do that. So how could this be? So we have, apparently we got some race condition in there. Now, just because we use these logs here. So that's really, really weird. Logs has been initialized. Okay, it's map anonymous, it's map shared. Prod read, prod write. And we are using these with sem init. Sure. In general, I would say it should work. We are not seeing this in a nice way. So let's change this one again. We had these sleep calls here so that we would be able to see something. So let's just try this. Race conditions are often difficult to debug with the debugger because the timing behavior can change and you want to find whether something happens in a certain order. You can do this with single stepping in a debugger, but this really heavily influences the timing and you might not be able to see the effect then. Consume buffer index sounds like an idea. We do that here. So it's generating numbers, but it's never consuming numbers. There's nothing that leads to the other process consuming numbers. So that's a bit odd. Oh no, there is now. Consume 1, 2, 3, 4. Oh, it's consuming them in a very weird order. Three, four, five, and it's also consuming them multiple times. So this is, why is it starting to generate these numbers again? So this is a bit broken. So clearly our program is not working correctly here. Okay, so what is going on? So our producer generates these numbers. It should just count up. Generated number, yes. Oh, this is a sneaky error here. If P2, and that's why you always add those braces here, these curly braces, so that you are sure that you never forget them. I mean, we forgot an if, so that means we had 2 producers and only 1 consumer, and of course then the number would not be the same as before. Let's try that again. Okay, so it looks better. And I will also check whether there's any of these processes still running. Main shared, just to be sure. Okay, nothing running. Producer, consumer, and then this one waits for the others to terminate. We should have 3 processes here, right? This one, here we have 1. Then after this, we have 2, where 1 runs the consumer. Then we have 1 again in this line here. Then we have 2 again in the fork, after the fork. And then we have 1 entering the producer function, and then 1 going down here into the wait PIDs. Okay, so this looks better. And we will now change this uSleep here to uSleep1 again, and this should run fast. Oh yeah, but probably we want to remove the print fs because now it's looking a lot better. Yes, so this looks exactly as before in the multi-threaded case. So the things that we changed, we moved the semaphores into a struct because that's more convenient, because then we only need a single mmap call down here for all the logs. We could, of course, do that with separate mmap calls, but then each log would consume 4 kilobytes of memory because that's the smallest unit that we can allocate. Could we put these into the same mmap? Yes, actually that would be nicer. So maybe let's still do that. So where is this buffer used? Maybe we also replace this one then. Buffer. So let's see. It would be nicer to have it in here. And the volatile, do we need it? Probably not. Probably the compiler understands what we want to do here. Okay. Buffer here. Yes, this one. And maybe also this one down there. Let's try whether it already compiles. Oh no, we forgot. Log struct has no member name buffer, but I added it there, right? Oh yes, we shouldn't do this. This is of course a mistake. Logs buffer. It now has a member buffer. So let's check where this is. Logs buffer should exist. Yeah? Oh no, plus, oh, this is an old error. So this is this one here. Plus equals buffer should be logs buffer. And then we have buffer again here. Now I think we got all of them. No, not yet. Buffer, one more. Okay, and now think about what we changed. We now changed this into a struct that contains both the logs and the buffer. So that means that this buffer will be protected by this log. We will also synchronize the programs with these semaphores that we use for counting. And all of this together is in the same mmap region. So that means that your logs and your buffer that you want to protect with these logs can be in the same mmap region. And that's quite interesting because, I mean, it's just memory that we allocate, and how we use it is the thing that matters for logging. As you may recall from one of the first lectures, if you use the lock on the toilet door, in the toilet door handle in a public toilet, but no one else uses the lock but bypasses it by jumping over the door, for instance, then of course it will have no effect. Okay. There were some questions. Why do we close the file descriptor if we don't? Do we see the questions? No, we don't see the questions. Let me check why not. Ah, yes, now we see it. Why do we even close the file descriptor then? We don't need to in all cases. File descriptors will also be usually closed at the end of the program. Unlink, however, is important. With SHM open, you create a file descriptor, so you have to unlink it when you don't need it anymore. Can you show us an example with execv, or should we use something different in A4? Oh yeah, let's do that, of course. Let's try something with execv. So, I mean, I think, did we already do that? Maybe not. So I will change this program here, and I will call this main execv. Of course. And now I will change this. I want to have an int argument count and a character pointer argv array. And I want to hide the Menti for a second, just so that we can see the code better. And now we won't use fork. And also the logs, or will we use fork? Yeah, maybe we will. Yes, so maybe I will create 3 programs now. Main execv producer, and I will also create a main execv consumer, and I will open all of them. main exec v. So I will also open this one, and I will also open this one. And my idea now is that this one here, the main exec v, will be the one that calls exec v consumer, and this one calls exec v on the producer. Let's do that. Of course, why not? And that means that the consumer has to just run the consumer function and not do anything else. Okay, so we can remove the producer here. We don't need it anymore. Oh, and that makes actually the program a lot easier, because now we can just take this code here, put it in the main. Oh, nice. Also, we maybe can we wait, with Unmap, we need to map this. We need to still map this somewhere. And that means we need to use a shared memory that is named, right? Because after exec, we will still have file descriptors, but we won't have we will still have file descriptors open, but we won't have the memory mappings, because memory mappings are replaced. Well, that means we need to use men shm open again. We just copy this in. I will do this a bit quicker now. If you want to learn more about shm open, then just check out the last lecture. There we covered that in more detail. So I will use shm open here. Open, and we open just some shared memory file here. So I will call this log struct. We will use o read write. We will also use what else do we need? We need some protection flags, and we need to check them out in open. With 2 or 3 should be fine. Oh, read write. Yes, and yes, I remember the shm open. The mode here, this is basically the file system mode that we want to use. So let's just use something like 640.644. This should be then read write for me, and you can check out some example also where this is used in in this form here, o create, o exclusive, o read write, and this is like the user permissions. So there are some definitions for these constants that boil down to these Unix permissions that you already might know. Okay, so yes, there's a question in the chat. Sorry, I'm late. Is this lecture for A4? Yes, A4. And if we find the time, then maybe also for A5. But we covered also some parts for A5 already. If you remember correctly, then if I remember correctly, then I think we covered linked lists already. So I will not cover the linked lists again. So we have the consumer here. We have our log struct. We open that. We get a file descriptor back. The file descriptor is now passed on to this one. We don't need this one anymore. Can later copy this over. Here we also want to open this file descriptor. We want to open it here with o create. And yeah, actually maybe also with some truncate flag or something. Let's check, is there some o truncate? If the shared memory object already exists, truncate to 0 bytes. Yes, why not? Let's do that. Truncate, and then the mode, yes, this one is defined. log struct. We need to truncate this also, ftruncate with fd 1096, should be fine. Then we unmap it. Let's just see whether this part works. I always like to check whether every step works. And will this part be published? I guess we can publish it, yes. Okay, we need to check out those flags again. I thought I included those. FCNT. Oh no, this was in the other program. Now I have too many files open here. So just trying to get this one to compile now. Yes, this one compiled, but it won't do much because we still have to exec the consumer and the producer here, right? So this doesn't do much yet. So in the consumer, we also want to map this. We don't care about the permissions actually, because we are not creating this file here. Then map shared, it is also fine. And in the producer, we do the same. There also, we don't need to initialize this again. We also don't need any of this code. We just run the consumer code, producer code in this case, producer code, and are done with it. So this is now, we now split the program, all the functions into separate programs. Interesting. So actually, I mean, take a look at it. Main function here for the producer, main function here for the consumer, and a main function here for the program that starts both of them. So let's copy in the header includes. Okay, and let's compile them. So we have, okay, we also want to compile the consumer. We also want to compile the producer. Okay. Okay, worked so far. And now we wanted to use exec to start them. And for that, we just use exec-v. Exec-v, we have our unistandard header that we need to include. We already included down here, so that's fine. We already do that. That means we can use exec-v right away. And we will take a look at exec. Exec-v is path name and arguments. That sounds about right. So let's use that. Exec-v. The path name is, we want to run main exec-v consumer. And the arguments, well, we don't need any arguments this time, so we can simply skip that. Or if we want to be super nice, then maybe we create an arguments array here. Say, well, arguments pointer array, and this arguments pointer array, we initialize this to, well, there's a convention. We can look that up. What's the first argument here? The first argument by convention should point to the file name associated with the file being executed. The list of arguments must be terminated by a null pointer. Good point. So we need to put a 0 here at the end. Okay, so let's do that. And we also copy that over here and run the producer. Okay, let's see. So this one, we need a semicolon here. And we need to pass the arguments, of course. And I want to try something. I want to try something here. What if I don't stick to this convention? Does anything bad happen? Let's try that. So I will just run, I just want to test whether so far my exec is working. So I'm just calling exit 0 here, and I'm also calling exit 0 here, just so that I know whether my code works. And I want to print here the argv array, so for size t I smaller than argc plus I, I will print the argument I. And this is something you should never do. Always provide a format code. Best practice, always provide a format code. If not, your program might be insecure, but you will learn about that in the master. Okay. Okay. But I think I've shown you several things that that might be insecure just to get started with learning all this stuff. So let's call it main exec v and let's check whether our exec works. Segmentation fault. Okay, what did we forget? Let's check what is going on. Segmentation fault. GDB main exec v run backtrace in line 88. Okay, so here we have our memset on logs buffer. Oh, of course, buffer. How did this ever work? This should not work, right? Because this is a size t pointer. It should be an array. I think before we didn't compile, otherwise it wouldn't have worked. It should be an array within the struct. Otherwise, there would be no way how this would get memory. Okay, so we should also fix that in our main shared. I'm pretty sure we didn't compile this one. Otherwise, we would have seen this error before. Buffer, and then let's move up this buffer size. This is a pretty combination that I use very often, like pressing Alt and then the arrow keys to move around the line can be very convenient. Okay, let's just check whether this shared example still works. So I'm searching now with Control R. You can search for a last prompt, and I will do that again. Shared. Yes, this one crashes also. So why does it crash? Let's check. Run backtrace in line 83. Yes, this also crashes here in the memset. Logs buffer. Oh yes, 4096 is way too much. This should be 16 times size of, well, whatever this is. This is a size t. So this is size t, size of size t. 16, that's the buffer size, right? Not 4096. The alternative is we skip this part here because we are zeroing it here anyway. So let's just remove it. Better. But this is not generally a recommendation. If some line crashes in your program, it's not generally a good solution to just remove the line. But in this case, this was necessary because the line was just wrong. Okay, let's run this again. Is there a website with all the most useful shortcuts? I'm not aware of any such website. And also, I think, so at least for me, it took me a long time to memorize all of them, because even if you hear about a shortcut once, difficult to remember all of them. For GDB, the ones that I showed were run, backtrace, and print. So let's maybe do that also again here. So I want to set up a breakpoint in the main function in line 83. That's also something that you want to do. Breakpoint in the main function in line 82. And you can also use layout ASM or maybe not layout ASM. Layout ASM is not nice. Let's use layout source. Layout source, and you can see the source code here. And if you now type run, then you can see it reached this breakpoint here. And what you can do now is you can use the step function to step through this code. And you can see, oh, interesting. So this is actually running through a lot of code in our program. Let's do this. So I want to step through the sem init. So you see there's no source available, it says. So, but it's actually executing some code here. Let's do this again, but with layout ASM, because maybe we just don't have the code for that. So let's step through that. Oh yes, you can see that here. Now it's in the function SemInit. You can see here, up there, you can see that it's in this function now. And this is assembly code that you will learn about also in this lecture. And this is assembly code, and we just stepped through this assembly code here. That was the SemInit function. And now we're back in the main function. Okay, let's switch back out to back to source, because assembly might be a bit more complicated to read. But those are pretty neat shortcuts. Backtrace. Maybe also here you can at any point use P to print something. For instance, print logs, print, well, I want to dereferent logs. And now you can see the members here. Buffer is 0, repeats 16 times. Buffer free elements. There are some data stored there. We can actually see these semaphores, what is stored in them. Can you also debug a program which hasn't been compiled with -G? Yes, to some extent, but it's I can show you the difference. So let's compile it without -G. Run this, break main, and then we want to break in main line 82 maybe. Oh, this looks different. So before it said this, now it says breakpoint 1 at this. Okay, this is already looking a bit weird. Let's also use layout source. No source available. Run. No source available. That means we didn't compile it with -G. There is no debug source included in this program binary. Okay. So, and that means that we can only switch to layout ASM. And what we have here is the ASM source code. And we can step through that again as before. So you can see here, we step through Unmap, we step through memset. You can actually see what memset does. You can step through SemInit, but you would have to read inline assembly code. Okay. Okay. Yes, there's some spam. Okay, but I mean, we all know spam from the internet. That's not our problem. So let's see. SemInit. What do we have here? Fork, consumer, producer. We want to go back to the execv example where we did exactly the same, but a bit differently. And there we also had this bug with the initialization, right? This memset was just nonsense because this buffer is way smaller than 4096 bytes. And we are setting it to 0 with this anyway, because we are setting the entire struct to 0, including this buffer here. Okay, let's see if we run this. And now I want to run the one with execv. And again, I'm pressing Ctrl R in the terminal. And this is really convenient to find the previous line. And I can press Ctrl R again, and it will search backwards to the previous to a previous call. If I run this, I mean, nothing happens. But that's to be expected, right? So we are running this. We are now, oh, this may be a problem. We are creating the file, but we are not deleting it. Log struct. Log. Okay, here it is. LA. I'm using Z shell, and there LA is a quite convenient shortcut for a list with some additional infos. The access permissions, this is read, write, read, this means 644, 00644. This is the username and the group. This is the file size. We can look up the file size just with that, the file name, and when it's last been modified. Okay, so let's see. We have created this file. I want to check what happens if I Shm unlink it down here. We want to unlink the def Shm log struct. Let's see what happens. Run this. Still there. Interesting. So why does Shm Unlink not work? Let's take a look at Shm Unlink. Maybe it will tell us what is wrong. Shm Unlink. The operation of Shm Unlink is analogous to unlink. It removes the shared memory object name. And once all the processes have unmapped the object, deallocates and destroys the contents of the associated memory region. After a successful Shm Unlink, attempts to Shm open with the same name fail. Interesting. Okay, so let's try that again. So maybe it's still there, right? Let's try this again with a clean setup. So we will remove this by hand. It's gone. Okay, so let's run this. We run this and it's still there. Why is it still there? Let's see. We have our Shm. Maybe because I passed this here. Maybe I shouldn't do that because I'm also not passing that up here. So let's just not do that. Okay, let's remove it. Let's compile it and we run it. Yeah, now it's cleaned up again. Very nice. So we remove the log struct afterwards, this pseudo file. This is not a real file. It doesn't really lie on the disk. So it also cannot grow arbitrarily large. It's in shared memory. Okay, so we have this here, we have this here, we have the mmap, we have our exec calls here, consumer and producer. And I wanted to check what they print, but they didn't print anything. Why didn't they print anything? Printf. Maybe I need to do that here as well. And this is like this is the consumer. And I want to have the same here for the producer. Okay, so this is like producer. Should be the same length. Nothing. Doesn't print anything. So that's a bit weird. It's not printing any arguments. Exec v main exec. Okay, so let's try whether this actually is working. Exec before exec v. Let's try it. After exec v. Should never be here. Exec v should never fail, right? That's what we believe. Before exec and then it's gone. Okay, so this part seems to work. Exec, consumer, but for some reason we don't see anything here. Oh, of course, we didn't initialize I. Of course, then it's uninitialized and it will have some bogus value. Let's try what value it has. Size ti. Let's try that. What value does it have? Okay. Yeah, I know that it's uninitialized. I'm doing that on purpose. 13. Of course. 13. Uninitialized values can be a problem. And you see, I didn't even get a warning here. Why did I not get a warning? This is not nice. I want to have warnings for that. Because I didn't compile with, I did compile with -w all. So that's a bit weird. Why I didn't get a compile error there. Or compiler warning. Now this looks better. So you can now see the producer printed main exec v consumer. Consumer printed main exec v consumer. Very nice. So what can we now do next? So, okay. Great. So this appeared to work, but we see that this is just a convention, and printing argv at offset 0 does not necessarily give you the program name. So if there are any bots, you can also flag other messages in the YouTube chat as spam. So just do that. If there are messages, just mark them as spam. Then I would say, let's fix that. Let's stick with the convention. It's nicer. And you can see now it's correct. Producer, consumer. And we will check whether this works. I mean, we can just remove the exit here, see whether this runs. Hope I didn't add any mistakes, but in general, the locking already worked before, so I'm expecting that it's now working as well. Maybe it doesn't. Interesting. So what could we do wrong here? Let's again check whether this is running at all. We need to just recompile it. Oh, buffer index. What did I do? Why did? Of course. This is now a compile error because I didn't use this line before. This should also be a. Oh, it's not a compile error here. Okay. Exactly. It's not running any of this. Log struct, read write. Read write, map shared, descriptor. This looks fine, basically, but why does it not work? Let's just try, just to be sure we don't mess this one up. No, they are really stuck somewhere. So that means we need to debug it. Let's again open a few windows. We start this one with GDB main execv run. Okay, we have our other processes. So this one is GDB -p 29397, and then we have. Okay, we are not allowed to do that. Okay, let's try it with sudo. We are allowed to do that with sudo. GDB -p 29398. Okay, and again, we are allowed to do that with. We should be allowed to do that with 29398. Yes, operation not permitted. Oh, this is a zombie. Interesting. So where are they stuck? Where are they stuck then? So apparently this one is the parent process. It's stuck in main execv in line 109. Okay, this one is stuck here. That's clear. Then we have the next process. This is the consumer. It's stuck in line 37. 37 buffer used elements. Okay. Interesting. Did we initialize these? Yes. We initialized these. But I've also never seen any generate message. I've not seen any of these messages here in none of these processes. So that's a bit weird. I should be seeing messages from these processes. If I'm not seeing them, something is wrong. So I'm compiling consumer, producer, and I'm also calling the right processes, I hope. Consumer and producer. Yes. Used elements is initialized with 0. Yes, because there are 0 elements in use at the beginning. So main execv. Why am I not seeing a single printf? Okay, so let's maybe check where they are. Printf. Waiting for an element to consume. Okay. And let's check what what we can do here. Generating a number. Okay. Okay, they are apparently waiting for each other, but no one is succeeding here. Yeah. But we definitely initialized all of this with 0. We created logs. We didn't really change anything, but split this up into producer and consumer. Okay, good question. What is wrong here now? Let's see whether it's actually ever going beyond that point of the sem wait. But also it's weird because they should be running here in a loop, right? Generating a number. The other is stuck, but this one here is actually terminating. So we just saw before that it was a zombie, right? We saw that according to the debugger. So that it's super weird because we didn't see the message that it finished. So how can it be a zombie then? So let's maybe just step a few steps further, generating a number. Actually, I think this is annoying, like going through this with printfs. Let's use a debugger. And for that purpose, we have to, we have to be a bit careful now. That's a bit tricky because we actually are starting this process now and not the producer. And off the top of my head, I'm now not sure how I set up a breakpoint in a program that is started by this program. Probably that is possible somehow, but I mean, it's a situation that you rarely need, that you set up a breakpoint in one program for another. Let's maybe add a printf statement here. Okay. Okay, so this one is executed, but never goes in here. So this is never 0. That's a bit odd. After generating this number. Okay, interesting. So it goes in there, it never returns from here, it never goes here. I think this one is crashing somewhere here in this with this access. Unmap. We have the f truncate here. Sure. Just give me a second before I continue debugging this. I will go through some questions on the Menti, and then I will try to figure out what the bug was. So please show an example with Shm Unlink. We did that. Then more help for A4. I think that's what we are working on. Should we use map anonymous in A4? If you find a use case for it, sure. If not, then not. Is it just me, or is the voice a few seconds before the picture? So from my side, it looks as if they are in sync, but if they are not, I will have to figure out what's wrong with this new setup here. Is there a good rule of thumb for when to use volatile? In general, if you use multiple threads in a program to modify one variable, then the compiler might not understand what you're doing. So then using volatile makes a lot of sense. In general, if the compiler shouldn't optimize this variable. If you don't use volatile, there might be cases where you need to use memory fences so that the compiler understands that a value in memory could have changed in the meantime. Shouldn't you show an example with execv, or should we use something different in A4? I think I did use execv, but I mean, execv now also wasn't that difficult to use in general. The programs are running. So shouldn't the name argument of shm open begin with a slash? Oh, yes, for best portability, it should start with a slash. That's correct. So you said if the parent process dies, the child dies. Yes. Yes, absolutely. If the parent process dies, the child dies, but that's correct. The child becomes the child of the init process. And that's actually also something we should check here. ps-fa grep for main execv. Nothing running. Okay. Okay, there's no such process running, because that would have been, of course, a mess if there would be multiple processes now and they interact in ways that we didn't intend. Yes, the process might continue running, but in general, if the parent dies, the child dies. My program compiles, but I still get 0 points. How is that? Well, compilation is not everything, right? I mean, if it compiles, that's not done. How come there is no main in A4? There's no. So I must say that I don't have the code. I don't know the code by heart. I would have to look at the code as well. But maybe this is something that we generate in the test system and add to your code. No, I will be back in Graz next year. The cat is far away. Yes, there will be no cat in the lecture, unfortunately, anymore. So do I understand this right, that we should have to use multiple of these 4 kilobytes as the length in ftruncated and Unmap in A4? I mean, you can't use anything else but multiples of 4 kilobytes, because that's the page size. That's what the man page says. If you don't believe the man page, you can try something else. How do I provide a file descriptor which I created with shm open in one function to another function without a return or anything? Pass by value, pass by reference, something like that? Sure. Yes, but that's not a question for the lecture, right? Okay. Let's see. Maybe, yeah, completely stuck on A4. I mean, just start with Unmap, get some shared memory running, maybe add exec and see whether you can get those two processes to interact. It's similar to what we do in the lecture here. We have a shared object which are all smaller than 4 kilobytes. Do we always need to initialize memory in length of 4 kilobytes? Yes, it's not possible to allocate anything smaller than 4 kilobytes with Unmap. It's not possible. Should we Unmap all structs at once in A4? If you can do that, I think that should be fine, but you probably want to ask that the tutor, because the tutor wrote the test cases, and therefore the tutor knows what should be done and what shouldn't be done. So let's take a look at our code again. So why is this one crashing? That's really a pity here. So let's see. So this one is running up here. Let's compile this again and we run this again before generating. So it's really this access here. Okay, let's try that. We just write this statement here and see whether it passes this statement. Let's try to understand what the problem is. Okay, so Let's try how can we trick the compiler into doing what we want it to do? Just make it look like we are doing something. Okay. But with the if, it didn't work. So let's try it here as well. Generate one. So that's interesting. So here it works, but down here it doesn't. This looks really weird, right? Because here it works, and then down there it doesn't. And maybe this one is optimized out. We can prevent that by adding inline assembly statement, for instance. That's what I call a memory fence. With that, you tell the compiler that something might have changed in memory. Please don't make any assumptions. Now it's stuck. Now it's stuck. So we got this. So let's try to access offset 0. Let's see whether this is already a problem. Yes, this is already a problem. Let's try to access buffer without dereferencing it. Oh, interesting. Buffer is wrong. So let's see what happens here. Printf logs. Oh, this starts making sense because this is a pointer and a pointer. Here logs buffer. This might not work. Okay, let's print this logs buffer. Let's print that everywhere. I want to print that right after the mmap here. So and here producer logs, and there we have the consumer logs, and then we also print that in the parent where we initialize the buffer and everything. So we print that here as well. Parent says this. Let's compile this, run this. Okay, parent says, oh, this is really broken, right? Logs buffer. Here it looks good. Of course. But in the other program, this doesn't work. Why does it not work? Because null is really weird, right? So what is logs actually? Printf logs, consumer logs, buffer. Oh, this one is not working. The mmap returns null. Can you see this? This is, oh, do we need to put the access permissions here? Still null. Why is that? Let me try one thing here. I want to use bin ls. I want to make sure that this file actually exists. Def shm log struct. Not that I mean, for some reason, I don't trust that this is actually working. Oh, it is working. Yes. Oh, I'm printing the wrong variable here. It should be logs. Okay, logs is initialized. Logs exists. logs buffer doesn't exist. So this is something that we can start debugging. So this is great. If you find something to start with, something to start debugging with, that's a great start. Okay. So we can see here buffer, and here it's buffer plus 60. Okay. So the offset here is 60, of course, because that's just an offset in this shared memory. Oh, but think about it, the buffer here, that's an array, right? So we Unmap that here. We mem set it to 0. And then we print it here. Oh, this should in principle work. Logs. Oh, we have to dereference it. Log struct, yes. What are we doing wrong? Logs buffer. So this is really weird that this one is correct. This one is not. Let me try one thing to debug it. I want to add plus 60 by hand here, and want to try whether this one would work without crashing. Okay, so no, this is not looking good because, I mean, this should be, let me cast it to a character pointer because I don't want to use pointer arithmetics here. Otherwise, this would count up by struct sizes, right? Okay, so this now by this logic would make sense. So why is buffer not this value here? Logs. Also, let me try this one here. Size T buffer, of course. We didn't fix our bug from earlier. Oh, no. So we got hit by a bug that we had in an earlier version. It has to be an array, not a pointer. Yes, the struct is different. But this is a dangerous pitfall, and we should avoid that. And how can we avoid that? Let's create another file, main exec v header. Of course. Oh, wait, this is main exec v consumer, main exec v header. And in that one, oh yeah, we can, of course, we can include all the numbers we need. We can create this struct. Okay. Oh, it's a very short header, just a few includes that we need anyway. And the struct and the buffer size. Sounds good. Let's remove this one and this one. All of this can go away. We just now need to include one header, and that's main exec v.h. Sounds good. Looks much simpler. I still want to declare this variable here. I could declare it in here, but it might look confusing because then you don't see where the variable is defined. But of course, you could do that. Okay, very nice. Now we are sure that they are all use the same struct, all use the same headers. Everything's the same now. Okay, let's run this again. But this, you see that by looking at this step by step, we slowly figured that something is wrong with this variable, and then we realized that, oh no, it's still the size t pointer. So by looking at the problems, you will be able to debug your programs and find the problems that occur. This looks much better. And this is actually, yes, they are generating and consuming, well, at least generating for now. Oh yeah, consuming, yes. So at least in very slow, it seems to work. So let's remove all of these printf statements because printf debugging is, I mean, not very good, but it's better than nothing. If we don't know how to debug it otherwise, it's a great idea to use printf. And especially for race conditions, printf sometimes is one of the best options because the timing changes too much if you run this with the debugger. Okay, so this is still, we still have some messages here that we can get rid of. Okay, just to check there's non-running, right? Okay, compiling, running. Okay, let's see whether we finished this example. Maybe yes. Great. So now we split up the program. We are using shared memory for the producer-consumer problem. And that's still basically the same problem. But you see that by changing things slightly, we get new challenges all the time. And it's getting, challenging again and again to get it working in a new context. This now looks pretty nice. I mean, we can get rid of these functions here in the main execv example, so we don't need them there. So this one just uses shm open, ftruncate, mmap, mem sets the area, initializes the semaphores, works the process, calls execv, calls execv again for the second process, waits for them to die. And then we could unlink, right? We should unlink, of course we should. But it will work just the same. We had a header file, which was also super simple, just 23 lines. Really, really short. The producer also, I mean, they barely don't fit on one page, but almost do. If I reduce the font size just a little bit, then it's just one page. And you can see you have a consumer here, producer here, and the execv parent process also here. Very nice. Okay, so now that this part works, let's check the Mentigen. And thank you, Ege, for noticing that the bug was that the structures were different. So will you not attend the OS SAP final event? Yeah, I'm still searching for a solution there, but I won't be here in January. So I can't join for any event in January. But I'm also not sure whether there will be an event in January because the numbers this year look much worse than last year. And the intensive care stations are filling up again. So I don't expect that there will be a final event in January. We might have to defer that to a later point in time. Why do you initialize the semaphores in each process? I don't. I hope I don't. Check, not that I do something wrong here. Am I initializing them in every process? I'm initializing them in this one. This is the process that starts the consumer and starts the producer, but they don't, right? They don't, yes, they don't initialize the semaphores. The consumer and the producer, you can open them side by side if you like, they don't use any seminit, so they don't re-initialize the semaphores. So let's hide the code again. Any news regarding the exam? Yes, probably it will be on December 3rd. But there will be an announcement. When do we get our A3 points? As soon as I got time to enter them. We are ready, but I was a bit a bit busy with moving, and I will get to that. Do we always need fork when using execv? If so, why? No. you don't. Do we have time for a quick example? Yeah, why not? I mean, we still have content for the next lecture. Let me open the execv example again. So this one, and I will save a single execv, or let's call it execv chain. Why not? I have an idea what I want to do here. And I will use execv here. Okay. And I will run this execv chain. I should have, I don't care, this header is fine, still works. I will create a chain of execv calls, and this one will call execv chain. And it will also sleep for 1 second because I don't want to kill my computer by running too many execs per second. And here I will just pass argv at, oh, how can we do that? So, I mean, there's a nice function, string to unsigned long. Very nice function. We pass it argv at offset 1. If, I mean, we could make some checks here, but only this is only for demonstration purposes. String to unsigned long. Let's check the main page for string to unsigned long. This one takes a pointer with the number pointer, then an end pointer, we don't need it, and a base is 10. Okay, so this gives us a unsigned long, unsigned long, oh, unsigned long, doesn't matter. Let's take this one. Unsigned long, if you need long, then it's this one, so this would be a 64-bit variable, then this would be a 32-bit variable on your current 64-bit machines. So we have argv here, argv offset 1. Argv is not a type name. What? Okay. Let's try to compile this and see what happens. Exec, yes, of course, we need to pass number here. Number, and then probably we also want to, yes, we want to print the number also again. So we want to print this number. Let's use a different function for that. Number string. So this number string will be, I don't know. I don't want to make it too small. We use sprintf with the u or something like, or u, for instance. We are very sure that this is shorter than this. Otherwise, so in general, writing code like this looks like it's very easy to run into trouble here. So we want to sprintf the number here, and sprintf, again, we need sprintf, a lot better is snprintf, of course. Let's check out snprintf. Okay. Okay, the snprintf writes at most size bytes. Yes, including the, yes, that sounds good. So snprintf, we take a format string, yes, and we take a size that's 128. Okay, number plus. And we pass our argument here, that's the number string. Okay, let's check whether this one works. Is c minus w. Oh, okay. Main. Oh, this is the execv chain. Execv chain. Okay, so this one pointer from integer. Oh yeah, it's nprintf. We always have to call the right function, of course. Okay, argument makes pointer from integer without a cast. Pointer from integer. Let's check again. Are we using it incorrectly? snprintf. Format, yes, of course. We want to pass here the number string. That's where you store it. Then the number of bytes, then the format string, and then the number argument. Of course, we should read the man page. Otherwise, of course, we run into trouble. So unsigned long. Okay, so let's make it an unsigned long. And we run this, the exec v chain. We start with 0. Doesn't look like it's working, right? Oh, but of course we need to, I mean, we are not printing anything. So maybe let's copy this code over from our consumer. We had this nice code here to print all the arguments. So let's copy them over. And this is the, we don't need this one. Let's just run this. Okay, so my code is not working well. But why? Printf my %s, and then we print the number string. Let's check why it's not working. Okay, this one apparently always is 0, number plus plus. Plus plus number, of course, otherwise we would pass the 0 value there again and again. This looks a lot better. Sounds good. Let's see what's happening. Okay, sounds good. We probably don't need the new line here. The new line is nonsense. Sounds good. And we also can run this with usleep 100, probably. Then we get a lot of execs per second. You see, you can use exec without fork. Okay, I just saw that the window is a bit cut off here, is it? Yes. That's not nice. Why is it cut off? It wasn't cut off before, so that's better. Okay. So yes, we can exam in real life or not. Currently, it's planned for a real life exam. The problem so the alternative is an online oral exam, and a lot of work with that many students. So hopefully we can do that written. It will be, I think, easier for everyone. I mean, most students don't like oral exams. Will there really be an exam with this many cases? What if there will be 2G? Will it still be in person? Yeah, tricky situation. If it's 2G, I would be less concerned actually than if it's 2.5G or 3G or something like that. If it's 2G, then I think we would be good to go. What's the best syscall? I don't think you can make a decision there. There are a bunch of syscalls without which you couldn't really run any program. For instance, write, read, that you need in every program. Otherwise, you couldn't write or read. User input. Will we get some example questions? Yes, but probably not this lecture because the lecture is at an end already. Can we do a 1G exam, please? I want to be safe. Well, I think 2G is still considered safe. But we will see. Maybe it will be online, but we have to decide that at a later point. So I would say thank you for being here. There are more questions, but it didn't show them to me. Okay. What if I'm not vaccinated, so I cannot attend the exam? Well, then either you get vaccinated or you do the exam as soon as it's possible in person. Again, I mean, that's 1G and online. No, basically, if it's offline, then it's offline. Do I understand this right, that the minimum length in Nmap is 4096 because of the page size? Yes, because of the page size. And what happens if we give a smaller length? Oh, there are some special cases. Imagine if you want to map a file and the file is smaller, and let's say it's like 128 bytes, and you want to map this file. Then the Unmap man page actually says something about that. Okay, let's see. Smaller. Yeah, file. The file mapping are initialized using length bytes starting at offset file. Offset must be a multiple of the page size as returned by this. You can use this function or syscall to check what the page size on your system is. Okay. Okay, so let's see. Let's check length. Maybe length. The length argument specifies the length of the mapping. There's no constraint on the length that it must be page size, but it's a special case if it's not page size. Yes. All pages containing a part of the indicated range are unmapped. Yes. Okay. Okay, so let's see. Here. Length was previously used in another, reserved using another mapping. Here, the range of bytes to be printed is specified by offset and length values again. So far in the man page, no special information on that. It will be of your concern in operating systems. So for now, you can just assume that this works. But in operating systems, you then have to think about how to handle that. So you have to think about, if the user wants to request 128 bytes, what do I do? Probably the OS would map an entire page. And then the question is, when writing back to the file, how much do you write back? Only the 128 bytes? Maybe the full 4 kilobytes? Good question. So that's then a design decision that you can make when doing the operating systems exercise. Okay, let's see. Okay. So this one is answered. Okay. Sure. I mean, yes. When I want to use SHM open, I always get an error. This is too big for a page size in this ASM. No. I don't think this error is on a standard Ubuntu or Linux installation in general. Are you please allowed to perform 2G check even if the exam is online? If the exam is online, then there is no such check. No. Vaccinated, but I'm not in favor of leveraging getting on with one's education to force them to get vaccinated. Oh, I mean, that's up to everyone for themselves. But I can only offer an exam. Like, if there is an offline exam, then that's your option, and you can go there as soon as you like. If the university says there's a 2G policy, then you have to discuss that with the university, whether you're allowed in or not. But that's not on me then. I don't make the rules who can go in or not. But you might have heard about this email from the rector, right, of Uni Klagenfurt, where the rector basically said, well, if you categorically say, like, vaccination is not an option, then it's difficult to align that with the goals of advancing science at a university. So what's your opinion on memory-safe languages like Rust, Zig, V? Do you think there's an advantage when your program is memory-safe and you don't have a garbage collector? Yes, I mean, memory-safe languages have big advantages. There's a reason why today we are writing a lot of code in memory-safe languages. Think about languages like Python, JavaScript, popular languages, right? C is not among the most popular languages. The problem is, as soon as you are interfacing with the operating system or with the hardware, also in other programming languages, in memory-safe programming languages, you might have to use these unsafe blocks where the language cannot really reason about what is happening because it's interaction with the hardware or the system. So in that case, you can still get in memory safety errors or other types of errors. Also, memory safety errors, yes, one type of bug. There will be others. As soon as you solved your memory safety bugs, there will be other bugs. There is a ton of bug classes that we don't solve with that problem. Does that mean we shouldn't use Rust? I think it's fair to try to use memory-safe languages, but on the other side, I also wouldn't expect that they are magic bullets that solve everything magically. We have memory-safe languages already for at least 3 decades, maybe even more. I think in the 70s the first memory-safe languages came up. Why haven't they changed anything so far? And I'm not saying Rust won't change this. Maybe Rust will. But this really raises the question, and why didn't any of the previous languages do that? Will the code be provided? Yes, I will upload it. Is there a reason why it worked to only Unmap the struct size for me and not? Yes, because Unmap will also round up the length argument. Unmap will internally make sure that at least 4096 bytes are mapped. You can try that. Try to Unmap a file and only map a small amount of a file and check whether you can read beyond this. So map like 13 bytes, check whether you can read byte 14, 15 and so on. I would be surprised if this seg faults. Really surprised if this seg faults. So maybe try that out. Okay, yeah, happy to do that again. If you prefer this late night time slot, of course, we can shift the lecture to this later time. If that is preferred by everyone, then we can do that. Otherwise, have a good night, a good evening, and see you in the next lecture. Yeah, but there are also other languages than Java, Python, and Go. For the OS space, it's even difficult to switch to CLang, from GCC to CLang for OS development. And if we would do that in operating systems, for instance, the code would get much uglier just by moving to CLang, because GCC has a lot of very nice extensions for C and C++ that make it super convenient to write operating systems. And if CLang already has this problem with LLVM CLang, then I don't see much of a change there anytime soon. CLang is not bad, but it's just not. It doesn't have all the years of development that went into optimizing it for OS development. GCC is just the primary choice there. Okay, with that, let me close the lecture. And if you have any more questions, just ask them on the Discord. And thanks for being here. See you in the next lecture. Bye.